don't want to miss my rant and rave on the recording, do you? So anyways, it was working like an hour ago, and then I said, okay, I'll just leave it. And then I went to try it just before class, and now it's not working again. So I don't know. Yeah, thank you for the reminder, Riley. I almost forgot to hit record. No stickers today, just little doodles. All right, so first things first, yeah, what is the point even? There's no stickers. Maybe there is in here, I have no idea. I can hardly use the pen stuff. Confession time. Please do the poll on Moodle by midnight tonight. It's only one question, so so hopefully not too bad, right? I'm just seeing if you want to have if you want to have 2 or 3 tests. So we've had 2 tests. We can call the little fun quiz a test, whatever. It was definitely test worthy. And so if you want to leave it at that and just wait until the final, then that's fine, right? If you want to have another test point, right? So if you want to have a 3rd test so that you've seen almost everything, hopefully I won't have time to get through the, I don't even know how to say them, Karnoff maps before this test on the 30th, if that's what you want. I don't know, the screen keeps doing stuff at me. It's confusing. So if you want to have 3, that's fine. We can do that. It would be on November 30th. If you want to just leave it and wait until the final, that's fine too. So your option number 1 is have another test on November 30th, which would cover everything since our little fun quiz, which was up until 4.2. So from 4.4 to 9.2, we'll get through trees this week. So 9.2 is on trees. We'll finish circuits today, which is 9.1. So kind of from 4.4 to 9.2, there's a lot of stuff that we covered there, right? We talked about kind of going between bases and all that kind of fun stuff, but and then of course the circuits and trees eventually. Oh yeah, chapter 9 is not on WebAssign yet, but it will be. Making a note to myself, post chapter 9 on WebAssign. Hey, it rhymes. At least something's working out today. So I'll post chapter 9, last assignments for chapter 9 on there. I've forgotten. Okay, so if you want to have another test on November 30th, it would mean that we could distribute the weight of the tests a little bit more, right? So we can kind of ease off some of the weights. I know the tests aren't weighted that heavily anyways. I can't remember what our weights are. 45, 30, and 25. Yeah, so your tests, I guess that's why I called it a little fun quiz. But anyways, whatever gets you the best grade is usually what I do. So this would would help distribute your grade a little bit more. Distribute your grade a bit more. But it also adds to your studying and your workload and all that fun stuff. So option number 2, which I totally understand if you want to me it makes no difference. So option number 2 is no more tests until the final exam. Okay. And so whatever you vote is anonymous, because I didn't want there to be any, oh, blah, 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 voted for this. No, no, no. So your vote is anonymous, just in case you feel like you should be voting one way, but you really want to vote another way. The final exam is, I think it's on the, I have one on the 11th and one on the 12th. Let me see here. The 11th. December 11th at 9 to noon. Good. Confusing because I do have one on the 12th, but it's not you guys. Oh, nice. 11th, 12th, 15th, 16th, they're riding you guys hard. 16th is a Saturday, so just beware. Exams are a half hour later on Saturdays for some weird reason. Messes with people a lot. All right, well, whatever the Saturday is, the time is going to be a half hour off of the normal schedule. Okay, so get your votes in tonight, or kind of ASAP. I saw there were a couple of votes already, so that's great. And then we'll just go majority rules. So, and then the majority decides the outcome. Oops. It is on Moodle. It's one of those like feedback microphone, or like, not microphones. Help me out. Oh, a little screen cone, yeah. A megaphone. Thanks, Zach. And Daniel, we're all just reaching. Yeah, a little screen cone or a megaphone. I do not know the average for the last test, but I think it should have sent out in the email. I think it was part of the stats. So check the email, and if it's not there, then ask me again on Wednesday. Yeah, so I mean, it depends on what you want to do. For review, I think the median and the mean were very similar, and so but good for you, Riley. As the statistician, I'm happy with that. It means that we're pretty normally distributed, so that's a good feeling. And I think they were pretty similar. Now I can't remember what they were. Okay. So let's do some review. A graph is traversable, right? Mostly reviewing terminology that you should have a pretty good handle on, or by the end of this week. So it's traversable if you can trace it, right, without lifting your your pen from the page and you hit all the vertices, but you only trace each edge once, okay? So if it can be traced in one sweep without tracing the same edge, more than once. And we also said that unlike the Hamiltonian cycle, right, we can pass through vertices more than once, right? It's the edges that we're concerned with for traversable. So vertices may be passed through more than once. And then we also found that it's going to be traversable if you have 0 or 2 odd vertices, right? And the degree of the vertex is how many edges go into that vertex, right? So that's from last day. So now we're just kind of using that. A graph is traversable if it has 0 or 2 odd vertices. Oops. Still getting the hang of this here. Oh. My writing wasn't that good to begin with. Okay. So then we kind of extended that to the Euler circuit. The Euler circuit is a traversable graph with the additional condition that we have to start and end at the same vertex, right? And so an Euler circuit is a traversable graph that begins and ends at the same vertex. It can't have any odd vertices, right, to be an Euler circuit. So in order to even be able to be an Euler circuit, you have to have no odd vertices. Right. So here, a graph is traversable if it has 0 or 2 odd vertices. So it can still be traversable if it has 2 odd vertices. One is the start point and the other is the end point. Whereas an Euler circuit is that special case where you have no odd vertices. And then we also talked about the Hamiltonian cycle, where we visit each vertex exactly once, right, and end at the original vertex. So visit each vertex exactly once and end at the original vertex. Struggling. Okay. We introduced the traveling salesman problem, right? And I posted that fun link where there's been some recent development on the traveling salesman problem. So TSP, the traveling salesman problem. Oops. visit each city, which is a vertex, right? So we can apply the traveling salesman problem to other problems as well, right? Maybe there's a lot of problems that you can kind of boil down to a similar problem where you have to visit each vertex exactly once and you don't want to go through the town again. So visit each city or vertex exactly once. Okay. And start and end in the same city. This makes it a Hamiltonian cycle, right? A Hamiltonian cycle. Okay. Oh, I just saw, sorry, I missed Dermot's question about, you sent an email. Yeah, you should have gotten an email from Gradescope when it was done marked. I can't remember when I finished marking. But anyways. Yeah. On the 19th. But who's counting, right? Good. On the 19th. Yeah, so it should have all the stats in there. Okay. So there are lots of different ways that have been developed to try to find the solution to a Hamiltonian cycle. And there's no optimal way, right? Yet they're working on it. Makes me think it's going to be very difficult, right? So what we're going to do is we're just going to produce or develop rather a few different ways that we can do it, and then you can kind of try different methods. Okay? So there are many different methods for solving a TSP. Right? Not all are optimal. Not all are optimal. The first way that we're going to introduce is called the sorted edge method. Okay, so first method is called the sorted edge method. Okay. What you're going to do first is you're going to draw your graph, right? Lay out your vertices, but also lay out the distances, or maybe it's the cost or whatever you want to minimize. Add that to each of the edges, right? So you can keep track of how expensive they are, whether that be distance or time or actual cost, right? It depends on what you're talking about. And so step 0, let's say, because this is going to be the step for all of these, right, is to draw a graph. So draw a graph showing the cities and distances, showing the cities and distances, right, or cost or time, right, whatever you're interested in. And identify the starting vertex. Okay. So that's where you're going to start for all of these. I probably shouldn't have put them in the sorted edge method, but that's okay. So step 1, which is part of the sorted edge method, is from your starting vertex, you're going to look at all the edges that are attached, and then you're going to go down the shortest edge, right? And so, or the cheapest edge, if you want to think of it that way. Okay? So choose the edge attached to the starting vertex, that has the shortest distance, or lowest cost, whatever you're talking about. Okay. And then travel along that edge to the next vertex, right? So now you go to the next city. Travel along that edge, or this edge, to the next vertex. And maybe I'll underline these. Whee. Just for emphasis. Step 2, so now you're at the next vertex, and guess what? You do the exact same thing, right? You go down the shortest edge. Okay. So the only hiccup is that you can't go back to where you started from until you've hit all the vertices, right? You have to travel through all the vertices and then you can travel back. So you don't want to close your loop until you're done, right? And so at the second vertex, travel along the shortest edge. Do not choose an edge that would lead you back to the original vertex or one that you've already visited, right? Because that's against the rules of a Hamiltonian circuit, but also the traveling salesman problem. So do not choose a vertex, an edge, I should say. Do not choose an edge that would lead you back, or that would lead you to a vertex already visited. Okay. Oops. This one that you've already visited, it includes the starting point, right? Includes the starting point, of course. You're going to keep going, just take the shortest edge. You do have to kind of have a little bit of foresight when you're looking at finding these edges, because if you feel like it's going to lead you back in a loop, then that's bad, right? You don't want to go down that edge. So step 3 is just continue until all vertices are visited. All vertices are visited and arriving back at the starting vertex. Back at the starting vertex. Well, even though it seems like it should give you some sort of optimal solution because you're constantly choosing the shortest edges, what happens is you might go short, 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 and then you have a choice, and picking the shortest one, you might have to, to get an optimal solution, you might want to take a slightly longer route because overall it's a shorter distance, right? And so one thing that I will say here is that we're going to note that the sorted edge method, which is the one we just discussed here, the sorted edge method, it is hyphenated, weird, may not produce the optimal solution. May not produce the optimal solution. So how did I start labeling these? Our second option is to use the it's essentially the sorted edge, but sometimes they can behave a little bit differently, right? And so this nearest neighbor method just says that you're going to go to the nearest neighbor, so you start somewhere, and then you just keep going to the nearest neighbor and until you go back to the start, right? So go to the nearest neighbor. I didn't do a very good job explaining that, but I will re-explain that in just a second here when we write this out. So you're going to go to the nearest neighbor and you're going to keep going. But what can happen is if the nearest neighbor is the original vertex, you're allowed to go back. So you can't go back unless the nearest one is the original vertex. Now, that can end up leaving out some of our vertices that we need to hit, right? So that's bad. But sometimes, I mean, it's an option if you end up hitting all the vertices. So go to the nearest neighbor and can't go back unless it is to the start, or starting vertex, I should say. Your third option, how was I highlighting these? Green. So the nearest neighbor method, not ideal. I kind of gave you these in order preference, right? We're probably going to use the sorted edge method because it's more defined. But our last method, I think it's our last one now, I can't remember. Because I wrote these last week. So we can use a brute force method. As you can imagine, mathematicians, computer scientists, yeah, we do it. Should we be using brute force methods? Probably not. It doesn't feel very good, right? It is an option. Yeah, brute force to get through it. Everyone's favorite options. It is a method. Actually, in the example that we're about to do, it's the optimal solution, which is not not great, but yeah, it doesn't scale well. Exactly, like you'll see in the example. Yeah, imagine you have 5 vertices, fine. You can brute force it, you can figure out the roots. Now you have 50 vertices. Yuck. Yeah, just brute force it. So the brute force method is a thing. I don't encourage it. We're going to look at it. Zach, I think Michael just answered your question, but in reverse order. You're typing at the same time. Okay. So so the brute force method, oops, not green. You check all possible roots. Yeah. It's amazing. So you're going to check all possible roots. One thing that's nice is going from Vernon to Kelowna to Penticton is the same distance as going from Penticton to Kelowna to Vernon. And so you can ignore the reverse options. How does that change things? Don't worry, we'll talk about it. Now I can't remember. I think it's n-1 factorial divided by yeah, n-1. It's on the next page. Stay tuned. So check all possible roots. We ignore reverse roots as they have the same distance and cost, as they have the same distance. Oops, a sign. Wow, what happened there? Same distance / cost. All right. So this is in terms of the brute forcing method, right, which came up in the chat here. So let's think about, so for 4 cities, right, we've got 4 cities like this, 1, 2, 3, 4. Okay. Let's say we're starting here, right, this is our first vertex. I have 1, 2, 3 different cities I can go to, right? And so let's see if I can figure out this pen because I want to lasso it, delete, and make room. So for 4 cities, there are first 3 cities we can go to. Right? And then there's going to be 2, then 2, then 1. Okay. Which means we have 3 times 2 times 1 roots that we can choose from, right? Because we've already started at the vertex, right? And so there's no root to start, and that would be why it's n-1. It's all coming back to me now. So we have 3 times 2 times 1, which is 6 roots. Okay. But half those roots we always say but. I don't know if you guys probably don't watch TLC, but if you do, no. when we drove across the country. The awesome part about staying in hotels is because they have cable. And so we always watch TLC. And anyways, there's 90 Day Fiance, and one of the clips that they kept playing was this girl. She was complaining because people were calling her butt cheesy butt. So whenever I say butt, call my butt cheesy butt. Anyways, 90 Day Fiance is so good. Anyways, so whenever I say butt, that's what I think of. Yeah, Eddie takes the criticism like a champ. So anyways, but half those roots are reversals of the others. So there are 6 divided by 2, which is 3 unique roots. My man has no neck. I don't know how it happened. Anyways, seems like a fun guy though. So now, right, we can do the same thing. So this was with 4 cities. So this was with 4 cities. Sorry, I don't have a pointer on here. Usually I kind of point, but there probably is one. I just don't know where it is. So this was with 4. So then we had essentially 3 factorial, right? So here we have 3 times 2 times 1 is the same as 3 factorial, right? So if we have n vertices, then we're going to have n minus 1, right? So if we let this be n equals 4, then n minus 1 factorial would be 3 factorial, right? So that's where the link comes from. So now consider n cities. Now consider n cities. You would have n minus 1 cities, n minus 2 cities, blah, 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 to 3, 2, 1 cities, which is n minus 1 factorial. Then we need to divide by 2. So there are n minus 1 factorial divided by 2 roots, unique roots, let's say. Okay. Yeah, he used it to condition his hair. But somehow he didn't get the memo that he was supposed to rinse it out. Like people do that, use mayo in their hair because it's like ultra conditioning. But then, yeah, you're supposed to just shampoo it out. But he just left it in. Yeah, nice. Makes for great TV though. So good. All right. So, let's do an example. Or actually, I'm going to add in what we kind of brought up earlier. For large values of n, the brute force method becomes unreasonable, right? So brute force method, we'll try it. And I'm kind of disappointed that it's the one that gives us the optimal solution, but anyways, that's okay. All right. For example, if we want to find the shortest trip, find the shortest trip starting and ending ooh, fancy, Ashley. Starting and ending in San Francisco. Oops, sounds, I almost wrote Frisco. Hey, now I really did write Frisco. That's not what I meant. Let me try again. San Francisco. Hard to say, for me, I guess. So find the shortest trip starting and ending in San Francisco, going to Sacramento, San Jose, and Fresno. Now, of course, right, we've got San Francisco, Sacramento, San Jose, and Fresno. We have 4 vertices, so we know that there's going to be, for our brute force method, pretty reasonable, right? We're only going to have 3 different routes that we need to brute force. So it's still kind of a viable option, but. All right, so the distance is San Francisco, which of course we will just abbreviate SF. I'll put Sacramento up here, which will just be an S. Gets kind of confusing when you use 2 letters for some and 1 letter for the other, but in this case we only have 4, so I feel like we can have a pretty good handle on it. San Jose down here, and then we'll put Fresno over here, which is over here. Okie dokie, artichoke. Let's see here. Between San Francisco and Sacramento, it's 96 miles. We can ignore units. I'm not gonna worry about them. I don't care. No, I do, but for us right now, we're just trying to figure out these distances. So then from San Francisco down to, oops, helps if I can see. Down to San Jose, it's 51 miles. Okay. Between Sacramento and San Jose, you can drive that route too. So what's interesting about these driving routes is there will be paths between all the cities, right? So this path is 129, and then from San Francisco to Fresno, clear cut here, we're at 189. Sacramento to Fresno, let's see if I can do it. 173, and then Fresno to back to San Jose, wait, is 151. Okay. So we're gonna start here. Okay. And then we're gonna list all our possible solutions. So we're gonna do the sorted edge method, the nearest neighbor, and then we'll do the brute force method to figure out what the total distance is for each of these combinations. All right. So for our solutions, the first one we'll do is the sorted edge. So the sorted edge solution says that I have to start in San Francisco. Okay, fine. All of these have to start in San Francisco. So from San Francisco, the sorted edge says that I'm going to go and take, let's go back and read through our little steps here. So step 0, draw the graph. We did that. Step 1, choose the edge attached to the starting vertex that has the shortest distance or lowest cost or whatever. And then travel along this edge to the next vertex. Okay. And as long as you're not taking yourself back in a circuit or back to where you started until you've hit all the vertices, you just keep going with the shortest edges. So what we're going to have, let's see if I can maybe copy. Uh-oh, I did not do a very good job. It's hard. Okay, copy. How do I paste? I know, but I've just got this. I've got the power in my hold down. Well, I'm just making a mess on my page. Okay, insert. How is it that I can copy and I can't paste? Yeah, the Microsoft gods, they're working for me right now. Anyways, okay, it doesn't matter. I was just gonna cheat and copy and paste the little graphic 3 times over. Yeah. Yeah, I'm not quite ready to commit to Bill Gates quite yet. Tap and hold your finger on the page where you want to paste the previously selected ink strokes, okay? Tap and hold your finger. Haha! Can't show history. Okay. Anyways, that was really good. We got close. I probably have to let it access my... Okay. Nice work, guys. Okay. Uh-oh. Hey, it went... Come on. I'm gonna give up. Oh, maybe I can move it here. Ooh. Okay. San Francisco's off the charts. That's okay. So the shortest edge from the starting point here is going down to San Jose. From San Jose, right, I'm gonna go to Sacramento. It's kind of a tight squeeze, right? It's either 129 or 150, 151. Yeah, it's San Francisco, so they've got it figured out. So then I'm gonna take 129, right? From 129 or from Sacramento, I've got the choice of going back. So initially the 96 miles back to San Francisco is the shortest edge. But remember, we can't go back until, can't go to San Francisco until we have all vertices, right? So then what does that mean? It means I have to go to Fresno, right? And then from Fresno, and maybe I'll do little arrows here. 1, 2, 3. From Fresno, now I'm done. I've hit all the vertices. So now I'm allowed to head back to San Francisco. And I'm not allowed to go through San Jose or Sacramento to get there, right? And so those are the rules of the game. So my fourth distance is the 189 from Fresno to San Francisco. Okay, so what does that look like? It looks like San Francisco to San Jose, which has a distance of 51. Okay. From San Jose to Sacramento, which has a distance of 129. Then we went to Fresno, which has a distance of 173. And then we went back to San Francisco, which was a distance of 189. So the total distance, and now I kind of flubbed it because I'm out of room here, but the total distance is going to be 51 plus 129 plus 173 plus 189, which is 542 miles. Okay. If we look at the nearest neighbor, which remember, it looks very similar to the sorted edge, except at any point, if it's the shortest edge, so from Sacramento down, we can go back to San Francisco because that's the nearest neighbor method. So our second method is the nearest neighbor. Let's see what we get. I'm going to see if I can Control B, okay. And then I'm going to move this over. If you okay. Which one? The first one, Dermot? So the sorted edge method, it says that you have to go and through each of the vertices. And without a pointer, it's really hard. So that's why you go through the first one. So you go from San Francisco to San Jose because your choices are between 51 and 96. So you're going to go 51. Right? From San Jose, you've got two choices because you're not allowed to go back to San Francisco yet. You have two choices, 129 or 151. So you take 129. So you go up to Sacramento. From Sacramento, you have two choices, 96, which takes you back to San Francisco, which is not allowed yet because we haven't hit all the vertices. So that means we have to go to Fresno. From Fresno, because we're not allowed to go back through cities, I have to take the 189 to San Francisco to get back because I have to start and end at the same point. Does that kind of make a little bit more sense? Okay, so now if we do the nearest neighbor approach, well, then we start here in San Francisco and then we go down to San Jose. That's our first one.
So for the second point, you take the shortest distance, right? For the second move from
yeah, are you talking about this nearest neighbor method?
The sort method. The one you did before, did you just did it for from
so this is the sorted edge method. Yeah. And then now we're going to go through the nearest neighbor.
The sorted edge method, when you make the second move, you have to take the shortest distance, right?
That's right. And you're not allowed to go back to vertices that you've already been to.
Okay.
Right. So the nearest neighbor is going to be very similar, but I'm allowed to go back as long as I'm going back to the starting point. So I'm not allowed to go through vertices more than once, but I'm allowed to head back if the shortest distance is to the starting point. So it's not ideal, because what we'll see is, okay, so same type of route, oopsies, same route, right? Our second move is from San Jose to Sacramento, but here in Sacramento, I have the choice between going back to San Francisco or going to Fresno, 96 or 173. Because San Francisco is the starting point, I'm allowed to take it because it's the nearest neighbor. Okay. So here, in this example, we are allowed to go back to San Francisco from Sacramento because it is the starting point. Because it is the starting point.
So this method allows us to go as multiple times to the starting point.
Yeah. And then, so now that we've hit the starting point, we're done. Okay, but notice that Fresno's left out, right? So let's see here. Hey, I've got a fun groovy. Fresno is not included. Uh-oh. Fun. Right, and so of course it's not an ideal route because Fresno's not included and we have this loop, right? And so we can't incorporate Fresno. So obviously the nearest neighbor approach is not going to be a solution.
How would you classify a solution if you go through all points?
Yeah. So it's only a valid solution if it satisfies the criteria, right? So we have to go through each vertex, and we're only allowed to pass through each vertex once, right? And we have to start and end at the same point. Joseph wants me to write in that color, all class. I know, it does add to the feel of it. Can you imagine looking back at your notes? There's a whole paragraph in just rainbow colored. So since Fresno is not included in the cycle, right, or the route, this is not a solution. The nearest neighbor method does not yield a solution. Okay. So how about the brute force method? So our third and final method that we're going to consider is the brute force method. Wow, I can't talk at all today. Tough when that's my job. So the there I go again, brute force method. This has to be one of those like linguistic things. Brute force method. Ugh. All right, so let's brute force this thing. Yeah, I keep putting the CE in earlier. Brute force. All right. So what we're gonna do is we just have to list all possible unique roots. Okay. So we know that we have 4 vertices, right? San Francisco, Sacramento, San Jose, and Fresno. So we also know that we should have 3 factorial, so 4 minus 1 factorial different roots. And then there's half of those are reverse roots. And so with 4 vertices, there are 3 factorial over 2, so that's 6 divided by 2, 3 unique roots. So we need to find them, right? So we need to find, so that's useful, right? So the reason that I'm telling you how many there are is because that will help you figure out when you're mapping them out, just to make sure that you've got them all, got to catch them all. So we need to map 3 unique roots, right? We need to find them all. So the first one.
Why did he use 2?
Pardon?
Why 2? Why divided by 2?
Oh, because half of them are reverse. So if you think about Vernon, Kelowna, Penticton is the same distance as Penticton, Kelowna, Vernon, right? Even though on paper they look different, they're the same, right? So that's why we're eliminating some of them, because they're just the same distance over again.
Thank you.
So that's why we cut them in half. Yeah, totally. Thanks, Nam. Good. That's exactly right. Just like 1 plus 2 plus 5 is the same as 5 plus 2 plus 1. Make sure you don't have any negative distances in there. You won't. There's no such thing. Okay. So let's see if I have any luck pasting this thing in. Now it just does it. It's like I had to train it a little bit. Okay. All right. So I brought this in so that we can have a look. So we have to start in San Francisco. So I know, and I have to end in San Francisco, right? So I already know 2 of these points. So my first one is going to go from San Francisco, and I'm going to do kind of a longer arrow, because I'm going to put the distances on the arrow probably. So San Francisco, and let's go down to San Jose first. Oops. From San Jose, I've got the choice between Sacramento or Fresno. It doesn't matter, we're gonna list them all, right? And so first I'm gonna do San Jose to Sacramento to Fresno to San Francisco. Okay, maybe I made my arrow a little too long initially. That's okay. All right, let's see if I can master this thing. Wow. Not bad for a newbie. Okay. So what I'm going to do is I'm just going to put the distances on top, And so San Francisco to San Jose, I've got a distance of 51 and 129. Sacramento to Fresno, 173, and then back to San Francisco, 189. So the total here is going to be 542 miles, right? That's the same as the sorted edge method.
You ended up with four numbers because you're ending with the starting point, right?
Yeah, so one of the conditions is you have to go back to San Francisco.
Right. So if we had a parabola 3 factorial divided by 4, which is equal to 3, would make it a total of 4 miles or whatever to be added to get the total miles. Or
so the factorials is referring to the number of vertices.
more vertices, okay. Well,
yeah.
That
so
is,
it doesn't actually care about the distances.
okay.
Yeah.
So in other words, 3 vertices are 4 edges.
Yes. I had to map it out.
So those are 4 edges there.
Oh, but we have, so here we have 4 vertices, right? 1, 2, 3, 4.
So these are, so what does the 3 represent then?
So the 3, so the number of unique routes that we have is because we have to start here in San Francisco, and from San Francisco I've got 1, 2, 3 choices.
Oh.
Right? And so the number of choices I have decreases every time I move, right? So it's 3 times 2 times 1 choices. And that's where the 3 factorial comes from. So it's actually 4 minus 1 factorial divided by 2.
Right. So I'm talking about the answer though, the answer which is 3 factorial divided by 2 equals 3. So I'm wondering if the 3 represents the number of edges, which is...
It's the number of unique routes.
Unique routes.
Yeah.
And what's that? What's a unique route?
So the San Francisco, San Jose, Sacramento, Fresno, San Francisco would be a unique route.
So San Francisco to the SF to SY is one route, and SY to S is another route?
No, this whole thing from San Francisco through all the cities back to San Francisco is one route.
Okay.
Mm-hmm. And the reason we're saying it's unique is because here, if you go from San Francisco to Fresno, Fresno to Sacramento, Sacramento to San Jose, and then back to San Francisco, that's also a route, right? But it's not unique because it's the exact same distance.
Oh.
Right?
So you're saying that there are 3 answers to this problem then, is that what you're saying?
Say that again.
Is that you're saying that there are 3 answers to this problem? Is that what you're saying? And this is...
For the brute force method, there's going to be 3 unique routes.
Okay.
Each with a duplicate going the other way.
And this is one of them?
That's right.
Okay.
Yeah. But brute force is not very nice, right? Because we actually have to we have to map out the routes, right? So it's not nice, but. So this is the same distance going backwards. Right, which is also a route, but it's not unique because it's the same distance. And here, what I was about to say is that this is the same as this is the same as the sorted edge method. Okay, right, so that's exactly what we found earlier. With the same distance, so it's still obviously a solution. Let's look at our map again. So the other option is from San Francisco, we could go to Sacramento. From Sacramento, I could go to San Jose or to Fresno. And so let's dip down to San Jose and then go to Fresno and then back to San Francisco. So another option would be San Francisco to Sacramento, which is 96. Gotta steal it on my page here, to San Jose, to Fresno, to San Francisco. Okay. So 96 and then 129. Let's see if I can steal them from up here. Okay, San Jose to Fresno is 151. Fresno to San Francisco is 189. And so the total here is going to be 96 plus 129 plus 151 plus 189, which I've just got 565 miles. And of course, going from San Francisco to Fresno, from Fresno to San Jose to Sacramento, and then back to San Francisco is the same distance. 565 is not better than 542, right? It's longer, in fact. So it's not an optimal solution. If we look at our last option, because we know there's only 3, we will look at San Francisco to Sacramento, and then instead of San Jose now, I'm gonna go to Fresno, and then from Fresno, I'm gonna go to San Jose, and then back to San Francisco. Some dog barking somewhere. So San Francisco to Sacramento is still 96. Sacramento to Fresno was 173. Fresno to San Jose is 151. And then San Jose to San Francisco is 51, which is 471 miles. Oops. And then of course, even though it's not obvious to me, when I have 4 vertices, seeing the reverse is actually pretty hard for me to do, at least. So seeing that San Francisco, Sacramento, Fresno, San Jose, San Francisco is the same as San Francisco, San Jose, Fresno, Sacramento, San Francisco, I don't see it. Hopefully you do. It doesn't matter. But if you do these arrows like I'm doing, then you can kind of convince yourself that, okay, all right, right? And so you could go through and list them and say, okay, well, from San Francisco, I could go to San Jose and then Fresno, and then I could go to Sacramento and then San Francisco. Let's see if I can remember what I said. Oh yeah, that's the reverse of the one I just did. I just did it and I didn't see it. So, but anyways, there's only 3 unique solutions. So out of all the solutions, .471 miles is the shortest distance. Therefore, it is the optimal solution. Not ideal when the brute force method is the one that gives you the optimal solution. And that's why it's so hard to solve these problems, right? Because there is always the option of, well, if I just brute force it, I might be able to find a better solution. But usually we like to rely on things like the sorted edge method. just because it gives us some sort of method, actual method for solving these problems. Okay.
So if we're going to be tested on these, would you give us a method to choose, or would we have to choose for ourselves?
I mean, in theory, you would have to choose. I'll probably just get you to do the sorted edge method, right? I'll say use the sorted edge method to do these. I want you to be aware of what the nearest neighbor is and what just the brute force method would imply or entail, but ultimately I'll get you to use the sorted edge method. All right, so we're supposed to start trees, but I actually feel like trees we can handle next day, and I feel like this stuff is pretty hard. So I'll post the assignment on WebAssign for 9.1. So this is the stuff that we just finished. So you have some practice there, and then we'll do 9.2 next day. How about? Cool. Any questions?
Gonna get a super easy test if we're gonna get a test for the next, if we're gonna be doing a test.